two separate instructions have been created for the purpose of working with functions which are exactly equivalent or somehow equivalent to the three instructions that we created in here. Those instructions are call and return. So both storing the RIP register and also jumping to that specific function, they are both encoded in one different instruction with the name of call. So in here, if I say call and then printing, it first saves or stores the value in the RIP, which points to the next instruction in here. And also in here, instead of jump, we say RET for returning. And what would happen is that it saves the RIP, but instead of R8 register, because it wants to make the general purpose register available to us, instead of R8 register, it uses a I guess less limited resource called a memory structure, which is called the stack, which we talked about before. But so what happens is that by saying call printing, first the RIP pointing to the next instruction in here would get saved in the stack, then the call would happen, the jumping would happen, we would get to the end of the function in here, then the return would pop that value out of the stack to the RIP register so that this instruction would get executed. So right now, if I press Ctrl O, hit enter and Ctrl X and just assemble and link it again and execute it, you see that we have a hello world in here. Also, I want to do it in the debugger too. So in here, I say gdb compare, break start, run, info, or actually a couple of step i's, step I and step I. Also in here, I want to run the object dump again. Now we are at the address of 4000 D8, which is this one. Now when the call happens, so let me just have a look at the well, RIP would be equal to 4000 D8, but when the call happens, the RIP would be equal to 4000 B0, which means the call has the jump encoded inside it. Now other than that, we said that it would save the RIP value inside another place, but this place would not be in the CPU and in the one of the registers, but it would be in some place in memory called a stack. If we want to see the top of the stack, if I say 1xg and then the RSP in here, it would give me the value of 0, 1, which means that we haven't pushed anything inside the stack. If I say step I and hit enter again, now we have jumped to 4000 B0, which means that the RIP would point to this 4000 B0. And if I look at the top of the stack, this is a place in the memory, right? Because if I say, pay attention, if I say N4 register RSP, it would give me the value inside RSP, which is actually the address of the top of the stack. You see, when I say $RSP, it would show me the content of the top of the stack. So this is a place in memory, right? And the content of this address in memory is this, just some random value. But the value inside the RSP register is a memory address. So the RSP register is always pointing to that specific memory address, which is the top of the stack. If I want to see the content of that specific place in memory or at the top of the stack, I use x /1xg and it shows me the value as a word. So in here, I could say x. As you see, when we want to see the contents of the register, we would use info registers and that register. If we want to see and look at a specific memory address, we use x command. X /, for example, 1xb would give me 1 byte at some specific location, which we should just provide the address. If we say 0x7ff and all of this in here and paste it, it's equivalent to say $RSP. If I hit enter, it shows me just 1 byte. If I want to say just one word and hit enter, it shows me this content. So this address or saying this command or saying $RSP are both equivalent. If I say if I hit enter, it shows me that at this specific location in memory we have this content 00000 4000 DD. Now what is 4000 DD? It is the address of next instruction. In the previous lecture we saved it in the R8 register, but in here using call we saved it in the stack, which is a place in the memory structure, and as you saw we could see it in here. Now if we say step I again, and don't worry about some of the commands in here, we might work with them, actually we would completely work with them in the exploit development section, but in here if I say step I, we go in the printing, step I again, step I again, I am at 4000 C4, which is this address after 2 or 3 more step I's. Now if you look, it says in the return in here, which is equivalent to C3 in the binary representation, this red would cause the RIP register to be restored. The value of 4000 DD would be popped out and would be saved inside the RIP register. If you look and I say info registers RIP, you could see the value is 0x4000 DD. Therefore, with a couple of more step I's, the system exit system call would happen and we would exit out of the program. Step I, step I, step I, and the process exited normally.